an autoregressive of order 2 and 0.9 and 0.4. And again, what this means is that we have 2 lagged sales. Postpaid 2 sales T minus, 2 plus our error term. So this is phi 1, this is phi 2. Yeah, this one's a little bit more subtle. It's kind of hard to, you look close enough, you can kind of see this falling and then rising again. I mean, I could see this and I could see that, but over here I'm not really seeing much. It's the nature of these cycles. If you're getting models that your predictions, you're not being able, if you've got data where you just can't model very well, it could just be this underlying cyclicality of the data of whatever it is you're looking at. And because we don't know what's causing the cycle, but we can see that it's there, that could be what's causing the poor fit of your models. All right, so let's check out the process itself. So this is, again, looking at the partial and auto and partial autocorrelation coefficients. Let's see, so we're seeing decay, right here, and it's coming back up, so we're seeing that decay. And we are, in this case, we are capturing the correct order because we've got 2 significant partial autocorrelation coefficients, and then they go to 0. So this, if this was our data, and again, it was pretty subtle in the cyclicality of it, but if this was our data, we would probably correctly identify this as an AR2 process off the bat. Unlike the other one where the moving average 2 process, we weren't really getting a very good indication of that. So let's again do the horrible. Again, bad.
You didn't even try.
Yeah.
Get out before you're not even trying.
It's almost embarrassing. But I can tell you this, as bad as this looks, and this goes back to day 1 of 580. As bad as this looks, the only way you're going to tell this is really, really bad is if what? You look at this picture. If all you do is have tables and regression coefficients and outreg and all that stuff, I mean, I want that stuff. But if you never look at the graph of how well your model fits the data, then you'll never know how bad it is. Because this picture tells us everything we need. I don't need to see your outregs. I don't need to see anything other than, this is horrible. So I've literally seen something as equally bad as this in practice, where I don't know if you took the class online or where you took it or whatever, but the first thing we've always done is graph stuff. First predictions we did was where we graphed our predictions and we saw how we're able to improve our predictions by adding dummies and account for seasonality and all that stuff. That's the first stuff we did. This is just, I don't know if it's just lazy or ignorance or a combination of the two, but if you don't look at this graph, you're never going to realize how bad this looks, because all you're going to see is, well, your R-squared is probably going to be pretty bad. There's our R-squared. Yeah, it is pretty bad. Less than 0.5% of your R-squared is, so less than 0.5% of the variation in sales is explained by your crummy model. So there should be signs in there that you have a crummy model, but I have seen people make mistakes that they shouldn't be making if they just took a little bit of time and graphed it. All right, so let's look at the residuals. We know the residuals are going to look bad. We know we're going to reject the null hypothesis that our residuals are white noise. We get a nice low p-value. So again, we got a pretty good clue as to the order of this. So let's run ARMA, second order ARMA process. Yeah, again, pretty good. Not perfect, but pretty good. Again, imagine, this is all made up data, but imagine if we had kind of our natural, our regular set of independent variables. So we had a price in there, for example, or we had income in there, or we had monthly dummies to account for any seasonality. So we're just saying that we don't know what's causing this, but we know how to model it, and we're doing a pretty good job of it. So it really is important to emphasize that this is a big improvement on what on our ordinary least squares regression. Let's check out the residuals. Again, you can see the red. They still seems to follow some of the pattern of the ordinary least squares regression, but we'll have to test them to see. So let's go to our Lejeune box Q statistic. And yeah, so we've effectively eliminated our serial correlation, improved the fit of the model, which is going to improve our forecast. Let's just, I skipped it, let's just double check this. So nice. Our auto and partial autocorrelation coefficients are all essentially zero. They're all within those 95% confidence intervals. All right. Hey, go ahead. Go. Score?
Was tied.
It was tied.
So
What was I going to say?
don't act like we're not. Come on.
Like you're not watching?
Not watching, just glancing from time to time.
As I said before, if it's a pure MA process or a pure AR process, they're pretty easily identifiable. It's when we start to combine the two that we have to go to that table. So let's try to find one. So this is, come on, I gotta have one. Here we go. Here's an ARMA process that it's the autoregressive component is of order 3, and the moving average component is of order 1. I'm going to construct the data and see what it looks like. All right, so pretty significant cyclicality here. All right, let's see if we can't identify it using our tools. So let's see, let's go back here. We know it's ARMA PQ. So we don't know what P is, we don't know what Q is. So we're looking for decay of some sort. It could be either direct, and by direct decay, we're talking about, all right, we're looking at that kind of direct decay, one-sided decay, or oscillating decay where it goes from here, and then here, or there, and then there, and there, and there, and there, and there. So that's oscillating decay. So one-sided decay versus oscillating decay. And that's the autocorrelation coefficients. For the partial autocorrelation coefficients, we're looking for oscillating decay beginning, oscillating or geometric decay beginning after the, after the first P lags. And P is the order of our autoregressive process. So, for the autoregressive component, the partial autocorrelation coefficients are going to give us a hint as into the order of our autoregressive component. For our moving average component, the autocorrelation coefficients are going to give us a hint as to the order of the moving average component. Did I say that right? It's written up here. All right, so here we go. Let's see if this helps. All right, we have decay, it's one-sided, and we said that, again, so we have decay, it's one-sided, and then for the partial autocorrelation coefficients, we have, it's kind of oscillating-ish, but it's got an abrupt decline after the first one. So, remember the partial autocorrelation coefficient gives us an insight into the autoregressive portion of our model. If this was me reading it, I would say it's an AR1 process, but we know that's wrong. The autocorrelation coefficients give us an insight into the order of the moving average process. So this doesn't seem to go to zero until, well, this is the case from the start. So after the first one, yeah, we've got our decay. So it looks, I would probably call this a 1-1 model, AR1, MA1. It's decaying after the first one, and it's abruptly falling after the partial autocorrelation coefficients. So it's yeah, it's not gonna help. Oh, okay, there. That's what it is. Oh, it's getting Disney. Okay, so we're getting direct decay after the first lag, after the first Q, and Q is the order of the moving average process. So that tells us it's an MA, the moving average portion is of order 1. We're getting oscillating decay after the first P lags. Again, oscillating decay after the first P lags. Yeah, I would say the first one falls, and then they start to oscillate. So they're not really oscillating until after the 1, 2, third one. Then they start to oscillate back and forth, because these are all on one side, right? So technically, we are getting kind of an insight into the order of the autoregressive process, but only because we're cheating and we know what the process is. Because again, those are supposed to be not statistically different from 0. Or they're not statistically different from 0. But like I said, we're kind of peeking at the answer, and then, oh yeah, I see it there. No, you don't see it. I don't see it. I would have guessed that at AR1, but I guess if you look, these are all on one side and they don't start to oscillate until after the third one. So, all right. All right. So again, let's assume that we don't we get the we use ordinary least squares regression. We get the horrible regression. We are going. We're not even going to check the residuals. We know they're going to be bad. We don't need to do that. Let's run our correct model. Again, pretty decent. Looks like we've eliminated any let's look at the Lejeune box Q statistic.
What was the measurement on the y-axis for that last graph?
For the
When
last
we're graphing
graph,
the sales against the,
yeah, all these are made up data sets, so
so it would be whatever quantity your sales did.
exactly.
Okay.
So,
I thought it was residuals from,
oh, those are residuals.
this one is, but the other ones you were doing.
Exactly. And again, we're just doing this so I can see if we're able to correctly model a process that we know, in which we know the nature of the process. So yeah, this could be sales changes, for example. All right. Another thing we can use is our information criteria. So we can use the Akaki and the Bayesian information criteria, again, to try to get us some more insight into the model. So this is all kind of the easy stuff because we know the answers. In actuality, we're not going to know the answer. So let's go to, let's see what this one. Which data is this? This is more simulated data. I don't want simulated data. I want real data. Yep. It says sales. All right, so let's see what we got here. This looks like quarterly data. And what we're going to do is try to forecast for this final quarter here. So, and again, this is, we don't know what the process is here, so we're just going to have to use the tools at our disposal. So let's look at our partial auto correlation coefficients. All right, one-sided decay, which is good. Starts off the bat, one-sided decay. And let's see, we have two, well, we have oscillating decay, right? Positive, negative, and then this looks like the geometric decay. It's all one-sided, and then it goes to the other side, and then, so remember the partial autocorrelation coefficients give us insight into the autoregressive portion, and the autocorrelation coefficients give us insight into the moving average portion. So AR2, MA1 perhaps, right? I'm just guessing. There's no answer key to these. We don't know the answer. All right, let's, all right, so, no, I don't want to do that. For some reason I chose 4. I think I'm gonna do different specifications, and we're gonna trim it down. All right, so it looks like I did I modeled it as a moving average, and I used a order 4. So notice I switched the commands, or I switched the options. So instead of the ARIMA, I put just the MA component. And 1/4 is going to be 1 through 4. Remember, moving average is just including the errors, lagged errors. So here's our lagged error terms. Let's predict, see how that turns out. Not bad. Not great, but not bad. This is kind of weird, but try to figure that out. All right. Let's check out the residuals. Let's see. It's just kind of a zooming in on that tail. So our prediction is consistently overestimating actual sales. It would be nice if we didn't do that. All right, so there's that huge error at the very beginning, which kind of throws off the scale, but it doesn't throw it off to the point where we can't see that there's a pattern in the residuals. So clearly we can see we're consistently underestimating and overestimating. We should do a test on this. Yeah, I I guess we did eliminate it. It's, we're failing to reject. No, I'm sorry, we are rejecting. Excuse me. So the model's an improvement. It's not bad, but we're rejecting, we still have zero correlation in the errors, which we saw. All right. Which means we should try another model. So let's do. Let's try a 1-1 model. All right. Both of our autoregressive as well as our moving average portion of the model are both statistically significant. Let's repredict. Let's see, what is this? Let's call it 1-1. Better? It looks better to me. Let's go to zoom in. So this is just zooming in on that last portion. Remember what I said, the last model was entirely overpredicted. Yeah. I said we going to be doing this, right? That's good here. I mean, there's some underprediction there, but we're kind of getting the look that we want. So this looks like a better model. Clearly, it looks like a better model. Let's look at the residuals. Pretty close to hovering around 0. Again, we get that huge error there, but we're not going to predict for the first period. And it's probably going to throw off our fit also. This. Yeah, so we get a nice big fat p-value. We failed to reject that. The residuals are white noise. Clearly, the 1-1 model is better than the moving average 1 through 4 model. We've successfully eliminated our serial correlation, improved our model fit, and hence will improve our forecast. You into a little secret. It's a secret that we like to tell ourselves. All right, so we do these and we look at this graph and we pat ourselves on the back and we say that's a pretty good model. Fit is pretty good, but in actuality, right, we're able to fit this data pretty well here, that last quarter of the data. So let's zoom in. Oops. We're able to fit here pretty well. The final quarter is not great, but we're underestimating a bit. But before that, the model fits pretty well. When you run a regression, including an ARMA process, when you run a regression, unless your model is really bad, like our OLS model and our to our data with the cycle in it, you're normally going to get a pretty good fit. So as long as you've got a pretty decent model, you're going to get a pretty good fit. And here's why. Notice I'm using the term one step ahead forecast. In essence, when we run a regression, it's kind of like what we were talking about before. And when we run the fitted model on the actual data, the model is following the data. So it's almost like you're looking at a question, you're looking at the back of the book, the answer, and then you're going back to the question and you're getting the answer right. What regression does is almost the same thing. It's following the data because the model is built to follow the data. Does that make any sense? This is where it makes sense. In a true forecast, there's no data here to follow. So that's really your test, is kind of a true forecast. And that's called a dynamic forecast as opposed to a one step ahead forecast. So the one step ahead forecast is when you're fitting a model on existing data, which we never do. Even if we were to do a holdback sample, it's still kind of cheating because it's going to follow the data again. So what we need to do is do a true forecast, which is called a dynamic forecast, which is going to basically eliminate the data from here and then see if we can forecast it. So it's even better than it's more accurate than a holdback sample, because a holdback sample, we're only going to use data for this period, but when we predict for this period, that data is still there and the regression is going to follow it again. It's still peeking at the data and saying, oh yeah, this is where it goes, this is where it goes. So that's why even using a holdback sample, our forecasts tend to be pretty good. With a true forecast, again, we don't know what the data is until the future. So we have to tell Stata to pretend that data doesn't exist and predict for it. And we can do that by just using a dynamic forecast option in Stata. That sounds confusing. Does it make sense though? Yeah. Okay.